Imagine, if you will, looking up at the vast cerulean dome that shelters our world during the day. It is a brilliant, welcoming expanse, painted in hues of blue, sometimes pierced by the golden blaze of our sun. Sunlight streams down, not as harsh, focused beams, but as a gentle, enveloping radiance that bathes landscapes in soft illumination, allowing colors to burst forth in vivid detail. This familiar spectacle is so fundamental to our existence that we rarely pause to consider its profound strangeness. How is it that such abundant light fills our terrestrial realm, transforming the very air around us into a canvas of brilliance, while the infinite cosmic ocean just beyond, teeming with countless stars, remains an abyss of nearly absolute darkness? This perplexing contrast, this fundamental dichotomy between the vibrant luminosity of our planetary home and the inky blackness of the cosmos, lies at the heart of one of the universe's most captivating mysteries. For generations, humanity has gazed upon the daytime sky and the nighttime heavens, implicitly accepting their disparate appearances. Yet, to truly understand our place in the universe, we must ask, why this profound difference? Why does a mere handful of kilometers above our heads, the boundless ocean of space, despite being awash in the light of billions upon billions of stars and galaxies, appear as a deep, impenetrable void? It is not merely the absence of the sun's direct glare that creates this cosmic darkness. It is a deeper, more intricate phenomenon, intricately woven into the very fabric of physical laws and the universe's grand design. We are poised on a precipice, a thin, shimmering boundary where light transforms from a focused ray into a diffuse glow, where the vacuum of space gives way to the bustling dance of atmospheric particles. This boundary is our atmosphere, a fragile gaseous envelope without which our days would be as dark as the deepest night, and the sky above would forever be a window into the unyielding blackness of eternity. On Earth, the experience of light is an immersive one. Step outside on a clear day, and you are surrounded by a pervasive illumination. Shadows are cast, yes, but even in their depths, there is a softness, a diffused glow that prevents absolute blackness. This is because the sunlight, having traveled millions of kilometers across the vacuum of space, encounters something entirely new upon reaching our planet: an atmosphere. This atmosphere, composed primarily of nitrogen and oxygen molecules, along with tiny dust particles and water vapor, acts as a colossal scattering agent. As photons, the tiny packets of light energy emitted by the sun plunge into this gaseous blanket. They collide with these molecules. These collisions are not like billiard balls. Instead, the photons are absorbed and then re-emitted in new random directions. This process, known as scattering, is wavelength dependent. Shorter wavelengths of light, like blue and violet, are scattered more efficiently than longer wavelengths, such as red and yellow. This preferential scattering of blue light is precisely what gives our sky its iconic color. It is light, redirected and diffused, filling every corner of our visible world, bouncing from molecule to molecule until it reaches our eyes from every direction, creating the illusion of a solid, luminous dome overhead. The air itself seems to glow, not because it generates light, but because it is densely populated with tiny mirrors and prisms, constantly catching and redirecting the sun's energy. Now let us contrast this vibrant, light-filled terrestrial scene with the silent, unyielding darkness of space. Imagine yourself suspended beyond the highest wisps of our atmosphere, perhaps orbiting our planet in a spacecraft. Below, the Earth is a shimmering marble, half bathed in brilliant blue, half cloaked in the velvet blackness of night. But above you and all around is the profound emptiness of space. The sun, when visible, is a searing, undimmed orb, a source of intense, unscattered light that casts razor-sharp shadows. Stars, no longer twinkling through the atmospheric veil, shine with a steady, almost unnerving intensity, like diamonds scattered upon an infinite black cloth. Yet, despite the presence of this blinding sun and countless distant suns, the space between them remains stubbornly, absolutely dark. There is no ambient light, no diffuse glow, no blue canopy. If you were to turn away from the sun, you would be plunged into a darkness so absolute that it would absorb every trace of illumination. A darkness more profound than anything experienced on Earth. This fundamental difference stems from the very nature of space itself. It is, for all intents and purposes, a vacuum. This initial, intuitive explanation that the atmosphere makes Earth bright and its absence makes space dark is a powerful starting point, but it merely scratches the surface of a much deeper cosmological puzzle. Why then, if space is filled with stars, does the night sky, even from Earth, appear dark? This question, famously pondered by the German astronomer Heinrich Wilhelm Olbers in the 19th century, forms the core of Olbers' paradox. If the universe were infinite in extent and infinitely old, with stars distributed uniformly throughout, then every line of sight from Earth should eventually terminate on the surface of a star. In such a universe, the night sky should be blindingly bright, a uniform sheet of stellar light, much like the sun's surface, rather than the dark, star-speckled tapestry we observe. The fact that our night sky is dark, even with billions of galaxies beyond our own, suggests that something fundamental about our universe prevents this theoretical cosmic luminosity. The darkness of space, whether viewed from orbit or from our planet's surface at night, hints at profound truths about the universe's age, its expansion, and the very limits of light's journey. To truly grasp this paradox and its resolution, we must first understand the fundamental nature of light itself. Light is electromagnetic radiation, a form of energy that travels through space in waves, but also behaves as discrete particles called photons. These photons are the universe's messengers, carrying information across vast cosmic distances at an astounding but finite speed. Unlike sound waves, which require a medium like air or water to propagate, light does not need a medium. It can travel perfectly well through the vacuum of space. However, for us to see light as a general illumination rather than just a direct source or beam, those photons must interact with something. They must either be emitted by a source, like a star or a lamp, or they must be scattered, reflected, or absorbed and re-emitted by other matter. In the vacuum of space, the density of matter is extraordinarily low. While there are certainly particles, interstellar dust, stray atoms, and energetic cosmic rays, they are spread so thinly across such immense volumes that the probability of a photon colliding with one is incredibly small. Most photons, whether streaming directly from a distant star or from our own sun, travel unimpeded for vast distances. They simply pass through the emptiness, carrying their energy and information in a straight line until they either strike an object, like a planet or a telescope mirror, or continue their journey across the cosmos indefinitely. Without a dense medium to scatter them, these photons do not create a diffuse glow. We only see the light if the direct stream of photons enters our eyes. This is why astronauts in orbit see pinpoint stars against a black backdrop. There is no intervening medium to scatter the starlight towards their eyes from multiple directions, creating a luminous sky. The light remains concentrated in the direct path from the star to their retina, and everything else is dark. So, the visible light on Earth, the very brilliance that defines our days, is a testament to the incredible power of interaction. The interaction between countless photons and the dense blanket of gas molecules that enshrouds our world. It is a constant, dynamic dance of absorption, re-emission, and redirection that paints our sky blue and fills our landscapes with a pervasive, gentle glow. In space, this dance is absent. The vast emptiness ensures that light, no matter how abundant at its source, remains largely confined to direct pathways, unable to coalesce into a general illumination. This fundamental distinction sets the stage for our further exploration, inviting us to delve deeper into the specific properties of Earth's atmosphere that allow it to perform this magical transformation, and to understand the deeper cosmological reasons why the universe, despite its fiery heart, chooses to whisper in darkness rather than roar in an eternal day. We are poised to understand not just the mechanics of light, but the very architectural principles of our cosmos, etched in the contrast between our bright blue sky and the profound blackness of the space beyond. The radiant tapestry of Earth's daytime sky is not merely a consequence of the sun's direct presence. It is a meticulously crafted masterpiece, woven by the intricate dance between sunlight and our planet's atmospheric veil. This gaseous envelope, a mere fraction of the Earth's total volume, performs an extraordinary feat, transforming focused beams of solar energy into the diffuse, omnipresent light that bathes our world in brilliant hues. Without this atmospheric intermediary, our days would be stark and alien, with the sun appearing as a blinding orb against a perpetually black sky, and shadows cutting through the landscape with an absolute, unforgiving darkness, much like the lunar surface. It is the very air we breathe that acts as a colossal natural light diffuser, orchestrating the luminous spectacle we so often take for granted. At the heart of this atmospheric alchemy lies a phenomenon known as Rayleigh scattering. Named after the 19th century British physicist Lord Rayleigh, this principle precisely describes how light interacts with particles much smaller than its own wavelength. Imagine a tiny photon of sunlight embarking on an epic journey from the sun's fiery core, traveling millions of kilometers through the silent vacuum of space. It carries a spectrum of colors, each corresponding to a different wavelength, from the shortest, most energetic violet and blue, through green and yellow, to the longest, least energetic red. Upon reaching Earth, this photon plunges into our atmosphere, encountering a dense, bustling crowd of nitrogen and oxygen molecules, which, crucially, are significantly smaller than the wavelengths of visible light. When our photon collides with one of these minuscule molecules, it is not simply absorbed or reflected in a mirror-like fashion. Instead, the molecule temporarily absorbs the photon's energy and then almost instantaneously re-emits it in a completely random direction. This re-emission is the essence of scattering. The key to Rayleigh scattering, and the reason for our blue sky, is that shorter wavelengths of light, the blues and violets, are scattered much more effectively and frequently than longer wavelengths, such as reds and yellows. In fact, blue light is scattered approximately 4 times more efficiently than red light. This difference is not trivial. It is the fundamental reason for the vibrant palette of our skies. As sunlight penetrates the atmosphere, the blue and violet components of the solar spectrum are scattered in all directions, essentially filling the entire sky with a blue glow. When we look up, regardless of where the sun is positioned, a vast number of these scattered blue photons reach our eyes from every angle, creating the illusion of a uniformly blue canopy above us. The sky, therefore, appears blue, not because the air itself is blue, but because it is redirecting the blue light from the sun towards us from every point in the upper atmosphere. The violet light, which is scattered even more efficiently than blue, contributes to this effect. But our eyes are less sensitive to violet, and much of it is absorbed higher in the atmosphere, leaving blue as the dominant hue we perceive. This pervasive scattering is why, during the day, light seems to come from everywhere, softening shadows and illuminating even indirect surfaces, creating a bright and welcoming environment. The phenomenon of Rayleigh scattering also elegantly explains the breathtaking beauty of sunsets and sunrises. When the sun is low on the horizon, its light must traverse a much greater thickness of Earth's atmosphere to reach our eyes. This extended journey means that an even larger proportion of the shorter wavelength blue and violet light is scattered away, dispersing across the vast expanse of the sky. What remains of the sunlight, the light that manages to travel a more direct path towards us through this denser atmospheric filter, is predominantly the longer wavelength colors, yellows, oranges, and reds. These are the colors that are least scattered and thus penetrate the thick atmospheric layer with greater ease. The atmosphere, at these times, acts like a giant natural prism and filter combined, stripping away the blues and leaving behind the fiery remnants of the solar spectrum. Furthermore, dust particles, water droplets, and other aerosols present in the lower atmosphere, especially near cities or volcanic activity, can further scatter and refract this remaining light, amplifying the reds and oranges, creating the spectacular, vibrant canvases we witness as the sun dips below or rises above the horizon. It is a daily reminder of the atmosphere's profound influence, turning a simple ball of gas into an artist of celestial proportions. Beyond merely painting the sky blue or red, the atmosphere is also responsible for the general ambient brightness that characterizes Earth's daytime. Even in the shade of a building or under a dense tree canopy, there is still ample light to see by, a soft illumination that fills the space. This is because the scattered blue light, along with other wavelengths that are scattered to a lesser extent, ensures that light permeates our environment from multiple directions. Every molecule in the atmosphere capable of scattering light effectively acts as a tiny secondary light source, diffusing the sun's energy throughout the entire volume of air. Imagine a room filled with smoke. Even if there's only one window, the entire room appears lit, not just the path of the direct beam from the window. The smoke particles scatter the light, spreading it around. Our atmosphere does something similar, but on a planetary scale and with greater sophistication due to the wavelength-dependent nature of Rayleigh scattering. This omnipresent illumination is crucial for complex vision, allowing us to perceive depth, texture, and color in ways that would be impossible in a world of stark, unyielding light and shadow. The density and composition of Earth's atmosphere are perfectly tuned to achieve this remarkable effect. If our atmosphere were significantly thinner, like that of Mars, the sky would appear a reddish-brown during the day due to dust scattering, and the sun would still be visible against a generally dark background, with stars potentially discernible even during daylight hours. Conversely, if our atmosphere were much thicker, like the dense, cloudy atmospheres of Venus or the gas giants, the sky would be perpetually overcast or feature a uniform, featureless haze, obscuring the sun entirely from view and creating a perpetually dim and diffused world. Our specific blend of nitrogen, oxygen, and trace gases, coupled with its particular density and depth, provides the ideal conditions for the striking blue of our days and the dramatic artistry of our sunsets. This delicate balance creates a light environment that has profoundly influenced the evolution of life on our planet, shaping the visual systems of countless species, including our own. Consider the role of clouds in this luminous symphony. Clouds, composed of millions of tiny water droplets or ice crystals, are much larger than the wavelengths of visible light. When sunlight interacts with these larger particles, it undergoes a different type of scattering called scattering, which affects all wavelengths of light more or less equally. This is why clouds, when illuminated by the sun, appear white. They scatter all colors of the solar spectrum back to our eyes in roughly equal proportions. When a cloud becomes very thick, it can block and absorb a significant amount of light, making its underside appear gray or dark. But its general effect is to further diffuse sunlight, creating overcast days where the light is even softer and more uniformly spread across the landscape. The interplay of Rayleigh scattering in the clear sky and scattering in clouds creates the rich variety of atmospheric optical phenomena we experience, from dazzling rainbows to ethereal halos. The very concept of daylight as we experience it, distinct from merely sunlight, is an atmospheric creation. Daylight implies a general illumination, an ambient glow that fills our environment regardless of whether we are directly facing the sun. This is the atmosphere's greatest gift. It takes a point source of intense light, our sun, and transforms it into a vast, diffuse light source that encompasses our entire visible world. It is this diffused, scattered light that allows plants to photosynthesize efficiently, reaching leaves and chloroplasts even in partial shade. It is this light that enables the vibrant colors of flora and fauna to be seen across diverse landscapes. It is the light that shapes our perception, our mood, and our very biological rhythms. Furthermore, the atmosphere protects us. Not only does it scatter visible light, but it also filters out a significant portion of harmful ultraviolet radiation from the sun, absorbing it before it reaches the surface. This protective function is just as critical as its light diffusing role, ensuring that the light that does reach us is not only beautiful, but also largely benign. The Earth's atmosphere is thus far more than just a blanket of gases. It is a dynamic, living shield and an artistic medium constantly at work, translating the raw energy of the sun into the life-sustaining and visually rich environment that defines our planet. Without it, our world would be a desolate, shadowed realm, a stark testament to the true nature of space, where light reigns only at its source. and darkness claims everything in between. The blue sky, the red sunset, the bright day. All are ephemeral yet enduring expressions of this luminous veil, forever shaping our perception of reality. Having marveled at the luminous artistry of Earth's atmosphere, let us now venture beyond its protective embrace into the boundless, silent realm of outer space. Here, the rules of light and visibility undergo a dramatic transformation. What appears as a bright, all-encompassing glow on Earth gives way to an almost absolute darkness, broken only by the pinprick brilliance of distant stars and galaxies. This profound void, this cosmic emptiness, is not just a backdrop. It is a fundamental characteristic that dictates how light behaves and how we perceive the universe beyond our planet. The key to understanding this darkness lies in the near-perfect vacuum of space and the staggering distances that separate celestial objects. The most crucial difference between Earth's atmosphere and the space beyond is the density of matter. As we explored, Earth's atmosphere is a relatively dense soup of molecules and particles, approximately 100 billion molecules per cubic centimeter at sea level. This high concentration provides ample opportunities for photons of sunlight to collide with and scatter off these tiny atmospheric constituents, filling our sky with diffuse light. In contrast, interstellar space, the vast regions between stars within a galaxy, is an incredibly tenuous environment. While not an absolute vacuum, it is remarkably close. The density of matter in interstellar space typically ranges from a mere handful of atoms, perhaps one atom per cubic centimeter, to a few thousand in denser regions like nebulae. This is billions of times less dense than the air we breathe. Intergalactic space, the even vaster stretches between galaxies, is even emptier, with densities sometimes dropping to less than one atom per cubic meter. Imagine a single photon of light emitted by a star. In this almost perfect vacuum, the probability of that photon encountering another particle, be it an atom of hydrogen, a dust grain, or an electron, is incredibly low. For all practical purposes, these photons travel in straight lines, unimpeded, for light years upon light years. They do not scatter off a medium because there is virtually no medium to scatter off. Consequently, the light from a star travels directly from its source to our eyes or our telescopes, without being diffused or redirected in any significant way. This is why, when you look at the Sun from orbit, it appears as an incredibly bright, sharply defined disk against a pitch-black sky. There is no atmospheric haze, no scattered blue light surrounding it. Its radiance is confined to its direct visual path. The absence of scattering in space means there is no ambient light. Ambient light is the pervasive, diffused illumination that results from light bouncing off countless particles and surfaces. On Earth, the entire volume of air above us effectively becomes a secondary light source due to scattering. In space, this mechanism is absent. If you are in the shadow of a spacecraft in orbit, that shadow is absolute and unforgiving. There is no diffuse light to soften its edges, no scattered photons to illuminate the shaded side. Turn away from the sun, and you are immediately immersed in darkness, even if countless stars are visible elsewhere in the sky. Each star, though a powerful emitter of light, is an isolated point source, its illumination strictly directional. Its light travels directly to you, and very little of it deviates to illuminate the space around it, or indeed, the space between you and it. Consider the immense distances involved. Even within our own Milky Way galaxy, stars are separated by vast stretches of empty space, typically several light years apart. A light year, a unit of astronomical distance, represents the distance light travels in 1 Earth year, which is approximately 9.5 trillion kilometers. When you multiply these immense distances by the trillions of stars in our galaxy, and then by the billions of galaxies in the observable universe, the scale becomes almost incomprehensible. The photons traveling from these distant sources have traversed cosmic voids for millions, even billions of years without interruption. Their journey is a testament to the emptiness of space. This sparsity of matter also means that the light from distant objects appears faint, even if the source itself is incredibly luminous. The inverse square law of light dictates that the intensity of light diminishes rapidly with distance. As light radiates outward from a source, it spreads over an increasingly larger area, so its intensity drops off proportionally to the square of the distance from the source. A star that is twice as far away will appear only 1/4 as bright. A star 10 times farther away will appear 1/100th as bright. Because space is so empty and light travels without significant interaction, only the light emitted directly towards our line of sight from these incredibly distant and inherently dimming sources actually reaches us. The vast majority of the photons emitted by any given star simply travel outwards into the void, never encountering an observer or another particle that would cause them to scatter and contribute to a general luminosity. So, while the universe is indeed teeming with light sources, these sources are sparsely distributed across truly colossal distances, and the space between them is a near-perfect vacuum. This combination leads to what we perceive as cosmic darkness. It's not that there's no light in space, it's that the light is concentrated at its sources and travels unimpeded, failing to create the ambient illumination we enjoy on Earth. When you look at the stars from Earth at night, you're essentially looking through a very shallow, clear pond, our atmosphere's negligible nighttime effect on starlight, into an infinitely deep, empty ocean where only the direct beams from far-off lighthouses are visible and the water itself remains dark. The sharpness of shadows in space offers another vivid illustration of this principle. On Earth, even on the sunniest day, shadows are never truly absolute black. The scattered blue light from the sky, along with light reflected from surrounding surfaces, provides a degree of illumination even within the shaded regions. This phenomenon is known as ambient occlusion. In space, however, where there is no atmosphere to scatter light and no significant reflecting surfaces for millions of kilometers, shadows are stark, crisp, and profoundly dark. An astronaut on the moon, for example, would see their own shadow as an intensely black silhouette, sharply defined against the lunar surface with no atmospheric scattering to fill in the darkness. The only way to illuminate the shadowed side of an object in space is with a direct secondary light source, such as a flashlight or the reflected light from another celestial body. This inherent darkness of space also has profound implications for observing the universe. Telescopes, whether on Earth or in orbit, are designed to capture the incredibly faint light from distant objects. To do this effectively, they must minimize any stray or scattered light that could interfere with the delicate signals they are trying to detect. This is why observatories are often built on high mountaintops, far from city lights, and above much of the light-scattering atmosphere. Space telescopes, like the Hubble Space Telescope or the James Webb Space Telescope, have the ultimate advantage of operating in the vacuum of space, where there is no atmospheric interference to dim or scatter the faint light from distant galaxies. Their images reveal incredibly detailed structures and incredibly faint objects that would be utterly lost in the atmospheric haze and light pollution of Earth-based observations. Ultimately, the darkness of space is a testament to the universe's vastness and emptiness. It is a canvas against which the cosmic drama unfolds, allowing the brilliance of individual stars, nebulae, and galaxies to stand out in sharp relief. This darkness is not an absence of light in its entirety, but rather an absence of the conditions necessary for light to be diffused and scattered, creating ambient illumination. It is a reminder that our experience of a brightly lit daytime sky is a unique planetary luxury, a product of our atmosphere's remarkable ability to transform the sun's focused radiance into a pervasive, gentle glow. Beyond our world, light travels mostly in solitude, a journey of countless photons across an almost unimaginable void, preserving the cosmic darkness that allows us to distinguish the individual points of brilliance that populate the universe. Our journey through the luminous veil of Earth's atmosphere and into the stark emptiness of space naturally leads us to one of the most profound and elegantly simple questions in cosmology. If the universe is truly vast and filled with billions of stars and galaxies, why is the night sky dark? This question, often attributed to the German astronomer Heinrich Wilhelm Olbers, who articulated it clearly in the early 19th century, encapsulates a paradox that challenges our intuitive understanding of an infinite, star-studded cosmos. It is known as Olbers' paradox, and it has perplexed thinkers for centuries, urging us to look beyond superficial explanations and delve into the fundamental properties of the universe itself. To truly appreciate the depth of Olbers' enigmatic question, let us first consider the assumptions that would lead to a perpetually bright night sky. Imagine a universe that is 1. Infinitely large, meaning it extends without end in all directions. 2. Infinitely old, implying that it has existed forever. And 3. Uniformly populated with stars and galaxies, meaning that, on average, the density of light-emitting objects is the same everywhere you look, no matter how far away. If these three conditions were met, then a truly bewildering scenario unfolds. Picture yourself gazing into the night sky from any point in such a universe. Your line of sight, extending outward from your eyes in any direction, would eventually encounter the surface of a star. This is similar to standing in an infinitely dense forest. No matter where you look, your gaze will inevitably land on a tree trunk. In this hypothetical, infinite, and uniformly populated cosmos, every patch of the sky, no matter how small, would be filled with the light of a star. The cumulative effect of light from countless stars stretching back into an infinite past and across an infinite expanse would mean that the entire night sky should appear as bright as the surface of an average star, perhaps even as bright as the sun itself. It would be a uniform, blinding sheet of light, utterly devoid of the comforting darkness and scattered pinpricks of brilliance we observe. The very concept of night would cease to exist. This conclusion seems utterly counterintuitive, directly contradicting our everyday experience of a dark night sky speckled with stars. And yet, the logic, given the initial assumptions, is remarkably sound. If the universe were truly infinite and static, every direction you looked would eventually lead your eye to the surface of a star, no matter how far away. While individual distant stars would appear fainter due to the inverse square law of light, there would be vastly more of them in more distant shells of space. The number of stars would increase with the square of their distance, perfectly canceling out the decrease in individual brightness. Therefore, the total amount of light received from any spherical shell of stars around an observer, regardless of its distance, should be approximately the same. Summing up an infinite number of these shells would lead to an infinitely bright sky. The paradox highlights a fundamental disconnect between a seemingly reasonable model of the universe and our observable reality. Early astronomers wrestled with this problem long before Olbers. Johannes Kepler, in the 17th century, suggested that the universe might not be infinite, or at least that stars were not uniformly distributed in order to preserve a dark night sky. Later, other thinkers proposed that perhaps interstellar dust and gas absorbed the light from distant stars, preventing it from reaching us. However, this explanation, while seemingly plausible at first glance, presents its own problems. If dust were to absorb starlight, it would over time heat up and eventually begin to re-emit that energy as heat and light itself, albeit at different wavelengths, still contributing to the overall brightness of the night sky and merely shifting the problem rather than solving it. Furthermore, if the universe were infinitely old, the dust would have had an infinite amount of time to heat up and radiate away this energy. So, the dust absorption theory, by itself, falls short as a complete resolution. The brilliance of Olbers's paradox lies in its power to force us to re-examine our most basic assumptions about the cosmos. It implies that at least one of the initial premises, an infinite universe, an infinitely old universe, or a uniformly distributed universe, must be incorrect, or at least incomplete, as our modern understanding of the cosmos indicates. The paradox, therefore, serves as a crucial intellectual tool, guiding us towards a more accurate and profound model of the universe. It demands that we consider the universe not as a static, eternal, and unchanging backdrop, but as a dynamic entity with a finite history and evolving structure. Imagine again that hypothetical, infinite, and eternal universe, uniformly filled with stars. Even if the stars were incredibly far apart, the sheer number of them, increasing with distance, would overpower their individual dimness. Consider it like this. If you stood in a forest and trees were infinitely thin, but also infinitely numerous, stretching infinitely far, eventually every direction you looked would be blocked by a tree. Similarly, in an infinite and uniformly populated universe, every line of sight would eventually terminate on the surface of a star. The apparent paradox arises because our direct experience of a dark night sky contradicts this logical conclusion, which is derived from what seemed like reasonable assumptions about the cosmos. This fundamental tension underscores the importance of observation and empirical evidence in scientific inquiry. While theoretical models can offer powerful insights, they must always be tested against what we can actually observe. The dark night sky, seemingly a trivial observation, becomes a profound clue, a piece of cosmic evidence that reveals deep truths about the universe's ultimate nature. It tells us that something is fundamentally different from the infinite, static, and eternal universe that some philosophical traditions and early scientific models once envisioned. The darkness is not an absence of interest, it is a profound presence, a signpost pointing towards a more complex and dynamic reality. Before we delve into the elegant solutions that modern cosmology offers, it is important to fully grasp the intuitive force of the paradox. We are accustomed to light filling enclosed spaces. A room, once a single light source is turned on, becomes generally illuminated as light bounces off walls, furniture, and dust particles. Our Earth's atmosphere, as we have seen, acts like a giant light-filled enclosure for us during the day. So, by analogy, it feels natural to assume that the universe, an even grander enclosure filled with vastly more light sources, should be similarly illuminated. The fact that it is not, that the vast majority of our night sky is black, is precisely what makes Olbers's question so potent and enduring. It forces us to confront the limits of our terrestrial analogies and to develop a cosmic perspective that transcends our everyday experiences. The paradox forces us to consider the very properties of light itself in a cosmological context. While light travels incredibly fast, its speed is still finite. It takes time for light to travel from distant stars and galaxies to reach our eyes. In an infinitely old universe, this finite speed would not matter, as light from even the most distant sources would have had an infinite amount of time to reach us. However, if the universe has a finite age, then light from objects beyond a certain distance simply has not had enough time to arrive. This crucial insight, which we will explore further, begins to unravel the paradox. Furthermore, the paradox subtly hints at the dynamic nature of the universe. If stars and galaxies are not merely static points of light in an eternal void, but are part of a constantly evolving system, then their distribution and properties might change over cosmic time. This leads us to consider the possibility of an expanding universe where the distances between galaxies are constantly growing and the light from receding objects is affected in profound ways. These concepts, born from meticulous observation and theoretical breakthroughs in the 20th century, provide the definitive answers to Olber's enduring question, transforming a simple observation of cosmic darkness into a cornerstone of modern cosmology. The darkness of the night sky, therefore, is not a mere observational quirk or an aesthetic choice of the cosmos. It is a profound piece of evidence, a silent witness to the universe's origin, its age, and its ongoing evolution. Olber's paradox, rather than being an obstacle, became a powerful catalyst for scientific discovery, pushing astronomers and physicists to develop a more nuanced and accurate picture of the universe. A picture that fundamentally differs from the static, eternal model that held sway for so long. The dark night sky is not a problem to be explained away. It is, in fact, one of the most significant clues to the true nature of the cosmos. The perplexing question posed by Olber's paradox, why the night sky is dark if the universe is infinite and teeming with stars, stood as a formidable intellectual barrier for centuries. It demanded a fundamental reevaluation of our most cherished assumptions about the cosmos. The elegant resolution to this paradox would not arrive until the 20th century, with the revolutionary insights of modern cosmology. It turns out that the universe is neither infinitely old nor entirely static. Rather, it has a finite age and is in a state of continuous expansion. These two profound discoveries provide the definitive answers to why we experience a dark night sky, revealing a dynamic and evolving cosmos far more intriguing than any static model. Let us first address the concept of the finite age of the universe. Our universe, according to the prevailing Big Bang theory, is not infinitely old. It had a beginning approximately 13.8 billion years ago. This finite age is a critical piece of the puzzle. Consider a star located 15 billion light-years away. Even if that star were incredibly luminous, its light, traveling at the speed limit of the universe, the speed of light, would take 15 billion years to reach us. Since the universe itself is only 13.8 billion years old, the light from that hypothetical star simply has not had enough time to complete its journey to Earth. It is as if we are standing in a vast, incredibly deep ocean, but we only have a limited amount of time to look for distant lighthouses. Many lighthouses might exist far beyond our temporal horizon, but their light has not yet reached our shores. This concept introduces the idea of the observable universe. Because light has a finite speed and the universe has a finite age, there is a maximum distance from which light could have possibly reached us since the Big Bang. This cosmic horizon defines the boundary of our observable universe. Any stars or galaxies that exist beyond this boundary, no matter how numerous or bright, are, for all practical purposes, invisible to us. Their light is still on its way or has not even begun its journey in a form that could reach us, having been emitted too recently or too far away in the distant past. Therefore, the night sky is dark in large part because there are simply not enough stars within our observable reach to fill every line of sight with light. We are seeing only a fraction of the universe, and that fraction, while vast, is not dense enough to create a uniformly luminous background. The universe, in effect, has a light speed limit and a time limit that together conspire to keep the night sky dark. However, the finite age of the universe is only part of the solution. The second, equally crucial piece of the puzzle is the expansion of the universe. In the early 20th century, observations by Edwin Hubble and others revealed that galaxies are not stationary in space. Rather, they are generally moving away from one another. The farther a galaxy is from us, the faster it appears to be receding. This is not because galaxies are actually moving through space in the traditional sense, but because the very fabric of space-time itself is expanding, stretching the distances between galaxies. Imagine dots on the surface of an inflating balloon. As the balloon expands, the dots move farther apart from each other, even though they are stationary on the surface. This expansion has a profound effect on the light traveling from distant galaxies to Earth. As light waves travel through expanding space, their wavelengths are stretched. This phenomenon is known as cosmological redshift. Just as the pitch of a siren drops as it moves away from you, the Doppler effect for sound, the wavelength of light from a receding object appears to shift towards the red end of the electromagnetic spectrum. This redshift has two significant consequences for Olbers's paradox. Firstly, redshift causes distant light to appear much fainter than it would otherwise. As the light waves are stretched, their energy is spread over a longer wavelength, reducing the amount of energy reaching us per unit of time and area. This means that very distant galaxies, already appearing dim due to the inverse square law, become even fainter due to the stretching effect of cosmic expansion. Their brilliance is diluted by the expansion of the space itself, making their contribution to the overall sky brightness negligible. It is as if their individual light bulbs are not only far away, but also steadily dimming as they recede. Secondly, and perhaps even more dramatically, cosmological redshift can shift the light from extremely distant objects entirely out of the visible spectrum. Light that might have been emitted as visible light by a distant galaxy billions of years ago could, by the time it reaches Earth, have been stretched so much that its wavelength now falls into the infrared or even radio portion of the electromagnetic spectrum, becoming invisible to the human eye. So, even if an ancient, incredibly bright galaxy were located at the edge of the observable universe, its light, though theoretically reaching us, would not appear as visible light to illuminate our night sky. It would contribute to the overall cosmic background radiation, but not to the visual brightness that Olbers contemplated. The interplay of these two factors, the finite age of the universe limiting the number of visible stars, and the expansion of the universe dimming and redshifting the light from those we can see, provides a comprehensive resolution to Olbers' paradox. The night sky is dark, not because there are no stars, but because the universe is young enough that light from beyond a certain distance hasn't reached us, and the universe is expanding, causing the light from those stars that are within our observable horizon to be stretched, dimmed, and often shifted out of our visible perception. We are living in a cosmos that is dynamically evolving, not a static, infinite, and eternally bright realm. This resolution has profound implications for our understanding of the universe. Olbers' paradox, once a puzzling anomaly, became a powerful piece of evidence supporting the Big Bang model. The observed darkness of the night sky is not a flaw in our understanding, but rather a direct consequence of a universe that began at a specific point in time and has been expanding ever since. It tells us that the universe is fundamentally different from what earlier thinkers might have imagined. It's a universe with a history, a timeline, and an ongoing narrative. Consider the immense energy that would be required to maintain a perpetually bright night sky. If every line of sight ended on a star, the total energy density of light in the universe would be enormous, likely unsustainable, and certainly far greater than what we observe. The dark night sky, therefore, represents a universe that is still relatively empty of light in a diffuse sense, a universe where the energy from stars is primarily concentrated at its sources, traversing the vast, expanding voids of space in isolation. Moreover, the darkness of space allows us to actually see the individual points of light that do reach us. If the sky were uniformly bright, individual stars and galaxies would be indistinguishable, washed out in a sea of omnipresent light. It is precisely because space is dark that we can discern the delicate structures of nebulae, the spiral arms of distant galaxies, and the individual pinpricks of light from stars in our own Milky Way. The darkness, in this sense, is not an absence, but a canvas, allowing the universe's true beauty and complexity to be revealed in contrast. It is the perfect stage for the cosmic ballet, where each luminous performer can shine in exquisite detail against the profound velvet of eternity. Even the cosmic microwave background radiation, an omnipresent glow that permeates the entire universe, does not contradict the resolution of Olbers' paradox. This radiation, a faint afterglow from the Big Bang, was indeed emitted when the universe was incredibly hot and dense, a state where it was opaque and filled with light. However, as the universe expanded and cooled over billions of years, the wavelengths of this primordial light were stretched so dramatically by redshift that they are now primarily in the microwave portion of the spectrum, far beyond what our eyes can detect. So, while the universe was once a fiery, luminous fog, its expansion has transformed that visible glow into an invisible microwave hum, further reinforcing the resolution of the paradox. In essence, Olbers' paradox forced cosmology to confront the limits of a static, infinite universe and to embrace a model of dynamic evolution. The dark night sky, far from being a simple observation, became a powerful piece of evidence, guiding scientists toward the understanding that our universe is finite in age, originating from a singular event and continuously expanding. This continuous expansion not only stretches the fabric of space, but also stretches the very light waves traveling through it, dimming their intensity and shifting their color beyond our visual perception. Thus, the darkness is not empty, but rather pregnant with information, telling a story of beginnings, expansion, and the sheer immensity of cosmic time and distance. It is a powerful reminder that our intuitive understanding of light and space, honed on a small planet with an enveloping atmosphere, must be profoundly adjusted when we look out into the true vastness of the cosmos. The dark night sky is an enduring mystery beautifully solved, a testament to the power of scientific inquiry to unravel the deepest secrets of existence. Having unraveled the cosmological mysteries behind the dark night sky, let us now turn our gaze towards the magnificent celestial bodies that bravely pierce this profound darkness, the stars and galaxies themselves. While the vast emptiness of space remains largely unilluminated, it is precisely this backdrop that allows the concentrated sources of light to shine with such breathtaking intensity and isolated brilliance. These stellar furnaces and galactic islands of light are the universe's beacons, each a powerful emitter of electromagnetic radiation, yet their radiance is sharply confined, unable to overcome the sheer scale of the cosmic void to create a general luminosity. At the heart of every star, an incessant, titanic struggle unfolds. These celestial behemoths are colossal spheres of superheated plasma, held together by their own immense gravity. Deep within their cores, unimaginable temperatures and pressures trigger nuclear fusion, a process where lighter atomic nuclei, primarily hydrogen, are forced together to form heavier ones, typically helium. This process releases stupendous amounts of energy, primarily in the form of gamma-ray photons. These photons then embark on an arduous journey, slowly battling their way outwards through countless layers of dense plasma, scattering and reabsorbing innumerable times until they eventually reach the star's surface. By this point, their energy has been transformed, emerging as a broad spectrum of electromagnetic radiation, including copious amounts of visible light. Our own sun, a middle-aged average star, radiates an astonishing 3.8 times 10 to the 26 watts of power, a number so vast it defies human comprehension. This immense output of energy is what makes stars such potent sources of light, capable of illuminating vast regions of space directly around them. However, once these photons leave the surface of a star, their journey through the vacuum of space is largely unimpeded. Unlike on Earth, where our atmosphere acts as a scattering medium, space offers very little to interact with. As we discussed, the density of matter in interstellar and intergalactic space is extraordinarily low. A photon emitted by a star will travel for millions or billions of kilometers, maintaining its direct trajectory until it either strikes another celestial body, enters a telescope, or eventually dissipates into the truly infinite reaches of the cosmos. This means that the light from a star travels as a concentrated beam, diminishing in intensity with distance according to the inverse square law, but not scattering to illuminate the intervening space. Imagine looking at a single powerful searchlight from a great distance in a perfectly clear, fog-free night. You would see the brilliant beam of light emanating from the source, but the air around the beam would remain dark. This is analogous to how starlight behaves in space. Each star is a searchlight, its light traveling in a focused path. We only perceive the light when our eyes or instruments happen to intercept these direct beams. The vast stretches of emptiness between the stars remain dark because there are no particles there to intercept and scatter the light towards us from multiple directions. The brilliance is highly localized, confined to the immediate vicinity of the star and the direct line of sight from the star to the observer. Galaxies, those breathtaking islands of stars, gas, and dust, are themselves concentrated sources of light, but on an even grander scale. Our Milky Way galaxy, for instance, contains hundreds of billions of stars, each a luminous powerhouse. Yet even within a galaxy, the immense distances between individual stars mean that the space between them is still largely dark. When we look at the Milky Way across its spiral arm from Earth, we see a luminous band of light stretching across the night sky. This is not because the space within the galaxy is uniformly lit, but because we are looking through a dense concentration of billions of individual stars whose combined light, viewed from our perspective, forms a glorious, diffuse glow. However, if we were to travel far into the interstellar void between two adjacent stars within the galaxy, the surrounding space would still appear profoundly dark, with only the direct points of light from nearby stars illuminating the scene. Beyond our galaxy, the universe is studded with billions upon billions of other galaxies, each a grand collection of stars. From the nearest, Andromeda, to the farthest observable galaxies billions of light years away, they appear as individual, luminous entities against the vast cosmic dark. Their collective light, immense as it is still insufficient to uniformly brighten the entire universe due to the immense distances, the finite age of the universe, and its relentless expansion, as discussed in the context of Olber's paradox. Each galaxy, despite its internal splendor, is an isolated beacon in a sea of emptiness. Other celestial phenomena also contribute to the universe's concentrated illuminations. Nebulae, vast clouds of interstellar gas and dust, can be spectacular sources of light. Emission nebulae, for example, glow brilliantly as the gas within them is ionized by the ultraviolet radiation from nearby hot, young stars, causing the gas to emit its own light in various colors. Reflection nebulae, on the other hand, do not emit light themselves, but reflect the light from nearby stars, scattering it to create a soft, ethereal glow. Dark nebulae, in contrast, are so dense with dust that they block the light from stars behind them, appearing as dark silhouettes against brighter backgrounds. Even though these nebulae can be visually stunning, creating illuminated patches within a galaxy, they are still relatively localized phenomena compared to the overall scale of galactic and intergalactic space. The light they emit or reflect remains largely confined to their specific regions, fading into the surrounding darkness over relatively short cosmic distances. Then, there are the most extreme sources of light in the universe: quasars and active galactic nuclei. These incredibly luminous objects are powered by supermassive black holes at the centers of galaxies, which furiously accrete surrounding matter. As gas and dust spiral into these black holes, they are heated to extreme temperatures, emitting jets of radiation and light so powerful that they can outshine entire galaxies. Quasars, which are essentially very distant and energetic active galactic nuclei, are among the brightest objects in the observable universe. Their light having traveled billions of years to reach us. Yet, even the light from a quasar, a truly monumental source of cosmic illumination, is still a concentrated beam that diminishes with distance and is subject to the redshifting effects of cosmic expansion. It does not magically illuminate the entire universe. It simply remains a distant, incredibly bright point against the dark tapestry. The contrast between these concentrated sources of light and the surrounding cosmic darkness is what makes astronomical observation possible and so deeply rewarding. Without the dark background, we would not be able to discern the delicate structure of a distant spiral galaxy, the intricate filaments of a nebula, or the subtle variations in stellar brightness. The darkness is not a barrier to observation. It is a canvas that highlights the luminosity of the cosmic actors. It allows our telescopes to gather the faint, direct photons from billions of light years away, building up images of objects that would otherwise be lost in a uniform glow. Consider once more the analogy of the searchlight in the fog versus the searchlight in the clear night. On Earth, our atmosphere acts like a fog, scattering light and creating a pervasive, diffuse glow that we call daylight. In space, the vacuum is like the clear night. The searchlights, the stars and galaxies are incredibly bright, but their light travels unimpeded and does not illuminate the space between them. This fundamental difference is crucial. It means that while the universe is overwhelmingly filled with radiation, particularly in the form of the cosmic microwave background, the visible light that could potentially illuminate space is too sparsely distributed and too strongly affected by distance and cosmic expansion to create the perpetually bright sky envisioned by Olber's paradox. Therefore, the isolated brilliance of stars and galaxies against the backdrop of an otherwise dark cosmos is not a contradiction, but a natural consequence of the universe's fundamental properties, its vastness, its emptiness, its finite age, and its expansion. Each twinkling star, each shimmering galaxy, is a testament to the localized power of nuclear fusion and gravitational accretion, shining brightly in its own cosmic corner, while the space between them eloquently speaks of the universe's immense scale and its profound, beautiful darkness. This darkness allows us to appreciate the individual points of light as distinct, wondrous entities, inviting us to explore their nature and their stories, illuminated against the ultimate canvas of infinite emptiness. As we conclude our journey into the perplexing contrast between Earth's daytime brilliance and the profound darkness of space, we arrive at a deeper appreciation for the epic journey of light itself. The story of light in the cosmos is not merely about emission and absorption. It is a narrative of immense distances, unimaginable timescales, and the fundamental properties of space-time. Understanding this timeless voyage of photons from their stellar birthplaces to our waiting eyes is the final key to grasping why our world is bright while the universe beyond remains largely dark. Light, in the form of photons, travels at a finite ultimate speed, approximately 299,792.458 kilometers per second in a vacuum. This cosmic speed limit means that when we gaze at a distant star or galaxy, we are not seeing it as it is now, but as it was when the light left its source. The farther away an object is, the further back in time we are looking. This is one of the most astonishing consequences of the finite speed of light and the vastness of the universe. Consider the star Proxima Centauri, our closest stellar neighbor beyond the Sun, located about 4.2 light-years away. When you look at Proxima Centauri, you are seeing light that began its journey more than 4 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is approximately 2.5 million light-years distant. The photons that reach our telescopes from Andromeda today started their journey 2.5 million years ago, long before humans walked the Earth. This means we are always looking into the universe's past, and the more distant the object, the more ancient the past we are observing. This time travel aspect of light has profound implications for Olber's paradox. When we look out into the universe, we are inherently limited by how long light has had to reach us. Since the universe itself has a finite age of about 13.8 billion years, there's a cosmic horizon beyond which light simply hasn't had enough time to arrive. Even if there were countless galaxies beyond this horizon, their light remains forever beyond our current reach, making those regions of the sky appear dark. We are literally seeing the universe as it was in its younger, less densely packed, and in many ways, less luminous state. The darkness, therefore, is not an empty void, but a temporal curtain obscuring parts of the universe whose light has yet to unfold upon our cosmic stage. The journey of a photon can span billions of years, crossing unimaginable distances. A photon emitted from a galaxy 11 billion light-years away began its voyage when the universe was only a quarter of its current age. It has traveled continuously, unimpeded by scattering in the vacuum of space across vast stretches of expanding space-time. During this immense journey, the very fabric of space through which it travels has stretched, causing its wavelength to lengthen and its energy to diminish. The cosmological redshift we discussed earlier. This stretching ensures that even if light from the earliest, most distant galaxies eventually reaches us, it arrives significantly weakened and often shifted out of the visible spectrum. What might have been a brilliant burst of ultraviolet light from a young, star-forming galaxy might now reach us as a faint whisper in the infrared, undetectable by the human eye. This means that the darkness of the night sky isn't truly an absence of all radiation. It is a lack of visible light from an infinite number of sources that would theoretically fill every line of sight. The universe is, in fact, bathed in a faint glow of microwave radiation, the cosmic microwave background, which is the redshifted afterglow of the Big Bang itself. This primordial light was once intensely hot and visible, but billions of years of cosmic expansion have stretched its waves into the microwave part of the spectrum, rendering it invisible to our eyes. So, while our eyes perceive darkness, sensitive instruments reveal that the universe is subtly humming with the energy of its ancient past. The finite speed of light also underpins our ability to actually study cosmology. By observing distant galaxies, astronomers are essentially looking at snapshots of the universe at different epochs. This allows them to reconstruct the history and evolution of the cosmos, tracing how galaxies formed, how stars evolved, and how the large-scale structure of the universe came into being. Each photon that reaches us from a distant source is a messenger from the past, carrying vital information encoded in its energy, wavelength, and direction. Without the finite travel time of light, the universe would appear static and unchanging, offering no window into its dynamic history. Furthermore, the emptiness of space through which light travels for so long is crucial for preserving the integrity of these ancient messages. If space were filled with a dense medium that scattered light, the photons from distant objects would be constantly redirected, blurred, and distorted, making it impossible to form clear images or accurately measure their properties. The near-perfect vacuum acts as a pristine conduit, ensuring that the light reaching us carries an almost uncorrupted record of its origin, allowing us to decipher the secrets of the cosmos with remarkable precision. The concept of light's journey also highlights the sheer scale of the universe in a human context. We live our lives in moments, seconds, and years. The geological processes on Earth unfold over millions of years. But the light from the most distant objects we can observe began its journey billions of years ago, when our solar system hadn't even formed, and Earth was a molten, inhospitable ball of rock. This vast temporal difference underscores our own fleeting existence against the backdrop of cosmic immensity. We are brief observers of a story that began long before us and will continue long after. In summary, the pervasive light on Earth and the profound darkness of space are not contradictory, but rather complementary aspects of a single majestic cosmic narrative. Our bright blue sky is a local phenomenon, a beautiful atmospheric trick orchestrated by the scattering of sunlight by a dense blanket of gases. It creates an immersive ambient illumination that defines our planet's days. The dark void of space, however, reveals the universe's true nature, its incredible emptiness, its immense scale, its finite age, and its ongoing expansion. The darkness we perceive in the cosmos is a direct consequence of light's finite speed and the universe's finite history, ensuring that light from beyond a certain cosmic horizon has not yet reached us. It is also a result of the universe's expansion, which stretches and dims the light from distant galaxies, often shifting it beyond our visible perception. This darkness is not a sign of absence, but a profound indicator of cosmic scale and evolution. It is a canvas that allows the concentrated brilliance of individual stars and galaxies to stand out, each a beacon telling a story of ancient fire and distant worlds. Its light, a timeless traveler through an ever-expanding void. The next time you gaze upon the deep indigo of the night sky, peppered with the sparkling dust of stars, remember that you are witnessing one of the most fundamental truths of the universe. You are looking back in time, seeing light that has journeyed for millennia and experiencing a darkness that speaks volumes about the birth, age, and dynamic nature of the cosmos. It is a darkness that makes the light truly visible, allowing us to contemplate the vast, intricate beauty of our universe. Thank you for joining me on this quiet journey through the science of light and darkness. If you found this exploration thought-provoking, please consider liking this video, subscribing to the channel for more such insights, or sharing your thoughts in the comments below. Your engagement helps others discover these peaceful journeys into the wonders of our world and beyond. For now, let your thoughts drift into the quiet vastness of the cosmos. Sweet dreams.